Okay, the last section of Chapter 7 has to do with the most common quantitative statistic that we use, which has to do with means. So we're looking at the means of the sample distribution mostly. So once we figure out what condition needs to be met, we will have the formulas for finding the mean and the standard deviation for the sampling distribution of the sample mean. We'll be able to explain how the shape of the sample mean is affected by both the shape of the population distribution and the sample size n. And then, if appropriate, we're going to use a normal distribution to calculate probabilities the same way that we did with proportions in the previous section. So when we look at this particular section, it's really important that you understand the difference between the population distribution and the distribution of the sample statistic. In this case, the sample statistic we're looking about is the mean of each SRS. So in this case, the population has to do with household earnings, and you'll notice the population is super skewed. It very often is that way, with a skew toward the right, with the high earners skewing that population, which means, of course, that your mean is tipped up a little towards the higher thousands. Now, when we're taking an SRS sample of size 100, in between this and this is the number of times that we have pulled 100 from the household earnings. We add them all up and we find the mean. And then here we have the distribution of those means. So when we choose a simple random sample from a population and we're looking at quantitative data, a mean is a really common one that we use. And so if we're comparing the mean of the population and the sampling distribution, a couple of facts occur. One is the mean of the sampling distribution is going to be the mean of the population. And the standard deviation of the sampling distribution, there's less variability in the sampling distribution, so we calculate that by looking at the population, standard deviation, and divide that by the square root of n, our sample size. As long as the 10% condition is satisfied. If that condition is not satisfied, there's a different calculator for standard deviation, which we don't learn, and you would just say that the 10% condition is not satisfied, so we can't use that formula. Now remember, there was some interesting pieces about proportion, but these facts hold true for the sampling distribution of the sample mean, whether or not the population distribution is normal. Doesn't matter what shape it is. If we're sampling from a normal population, then everything we can assume about a normal population, we can also assume about that sample distribution. So the population is normally distributed with a mean and a standard deviation of x bar and sigma. Then the sampling distribution will have those exact same things, except the standard deviation has to be divided by the square root of n, once again, providing that the 10% condition. So sometimes the population is not at all normal. So you're wondering, well, what can I do now? But most population distributions aren't. But when we look at the sample distribution, particularly of the mean of the sample distribution, we find that the shape of the distribution as the sample size increases becomes more and more and more normal. And so when the sample size is large enough, the distribution of the sample means is very close to normal, no matter how skewed the original population distribution is. And there's this important component that you have to have a finite standard deviation. Just you'll read that, and that just means that there's a specific one. It's finite. So the central limit theorem, this talks about what will happen when n is large. The sampling distribution of the sample mean is approximately normal. And you did a little work, kind of. Here we've got a population distribution. I have no idea what this could possibly mean, and it's quite weird. It doesn't have a clear center. It's trimodal. It's got a bunch of stuff up toward the top. I mean, it's just a bunch of stuff weird. But then, as they are collecting SRSs from this an n of 2, an n of 5, of n of 10, of n of 25, by the time we've taken enough simple random samples with a high enough n, and they have a capital N here, but that really means the lower n, the sample size, it approximates a normal curve. And so we're going to basically, most of them, even really skewed ones, will be fine at 25. But, so here we've got, the central limit theorem basically says that if it's a super skewed thing, if you can get your n to be greater than or equal to 30, you can treat it like it's normal. So all the things we know about using normal CDF and all of those things, we can use if our sample size is 30 or above. And for most things that are a little bit skewed, 25 is plenty. So assuming all of those requirements are met, the 10%, the central limit theory of greater than 30 for our n, you can go ahead and here is your how you calculate the standard deviation of our sampling distribution, and here is how we calculate our mean. And then we can go ahead and use the work that we're used to doing with normal calculations. And there you go, and we'll do some samples in class.